Okay, now we're going to look at velocity vectors in 3 dimensions. Okay, let's look at instantaneous velocity in 1 dimension before we try to tackle 3. And this is a bit of a review, but if I have a point here and a point there, if I connect those two with a straight line, I know that the slope of that line is going to be given by a delta x over a delta t, and that's going to be my average velocity. So the slope of the line between any 2 points on a position versus time graph is going to be the velocity. But if I want to know what the velocity is at a particular instant in time, I need to take the limit as my time interval goes to 0. So I let my time interval get smaller and smaller and smaller and smaller. And as I do, this line between those 2 points converges to become a tangent line at my point of interest. And the slope of that tangent line is the velocity at that point. And we know that that's going to be given by the derivative dx over dt. And so that would be my instantaneous velocity, the derivative of the position function with respect to time. And we know on any position versus time graph, the velocity is going to be, the instantaneous velocity is going to be given by the slope of the tangent line at every point. So if I picked a different point, say a point up here, there would be a different tangent line, one that just kissed that curve at that one point, not intersecting any of the others, and the slope of that line would be the velocity at that point. Now let's extend this to 3 dimensions. So I've got this blue or teal curve, which is just this curving path in space, and I have picked a position vector, which I've called R1, and that R1 is going to a particular point in space. Now you can imagine some object that's following this path, and so I pick it up here at R1, and it goes to another position, it goes all along the path. So I can pick another point on that curve and draw an R2. And so I've got R1, which is a position vector to one point, and R2 is a position vector to another point. And in 3D, the displacement works exactly the same way. So I can draw a vector from my initial position to my final position, and that would be my displacement vector, delta r. And of course, that's the vector from where you start to where you end up. And it would be the vector subtraction r2 minus r1. That would be r2 vector minus r1 vector. And it works the same in 3 dimensions as it does in 2 or even 1 dimension. The definition of displacement works the same way. So we have our displacement vector delta r, which is r2 minus r1. And of course, we call that the change in position. That's what that symbol delta means, change in. And that's our displacement vector. Now, what is R2? What is R1? R1 is going to be a vector that's going to have some value x1, y1, z1, and those would be the x, y, and z coordinates of those vectors. And similarly, R2 would be some x2, y2, z2, and that would be the coordinates of the vector R2. And so those are the points that those vectors point to, and of course I can use those as the components in the vector notation form that we've seen with x hat, y hat, and z hat. So I can simply say that my R2 vector is x2 in the x hat direction plus y2 in the y hat direction plus z2 in the z hat direction, and similarly for R1 with the components x1, y1, and z1. And again, remember, these are just numbers. You know, x1, y1, z1, that could be 3, 7, minus 4. Whatever numbers they point to, that would be the numbers of those components. Now, if I take this delta r, that's going to be the vector subtraction. And so I would just subtract these 2 vectors here. And so how do you do that? Remember, you group the like terms. So I've got my x hat terms together, and so r2 minus r1 is going to be x2 minus x1 times x hat. So that will be the first term for delta r. We can say that delta r vector is going to be x2 minus x1 in the x hat direction. And then we'll have the same thing for y hat direction will have y2 minus y1. So that would be plus y2 minus y1 in the y hat direction. And then we'd also have the final case of z2 minus z1 in the z hat direction. But what is x2 minus x1? That's just delta x. What is y2 minus y1? That would be delta y, and so on. And so we can write our delta r in terms of x, y, and z. So again, we have our delta r here, and we can write it as delta r is equal to delta x in the x hat direction plus delta y in the y hat direction plus delta z in the z hat direction. And remember, what's delta x? It's just x2 minus x1. This would be y2 minus y1. This would be z2 minus z1. And just like we did before, if I want to find the average velocity, I just take my delta r and I divide it by delta t. And so I would have my delta x over delta t, because I'm taking this term, dividing it by delta t. I take this term, divide it by delta t. That gives me delta y over delta t. And of course, delta z divided by delta t gives me that term. We keep the x hat, y hat, and z hat unit vectors. And I can make a definition that my delta x over delta t is just Vx, and Vx is the x component of the average velocity. And so I can do the same thing for Vy and Vz. And so that gives us the way to calculate the average velocity in 3 dimensions. We just do the same thing we did in 1 dimension 3 times. Delta x over delta t, delta y over delta t, and delta z over delta t. So let's look at an example now. We have this example. A mass is initially located at a position r0. 0 is sometimes used for the initial position of something. It stands for the position of it at t equal to 0. That's why it's often used for initial position. So my initial position vector here is 3 in the I hat direction, minus 4 in the j hat direction, plus 2 in the k hat direction. So I'm using the I hat, j hat, k hat notation here. I mentioned that I want you guys to be fluent in using both it and the x hat, y hat, z hat notation. So I'm going to mix these up into a problem so that you get a good opportunity to work with both kinds. But just remember, it goes in order: x, y, z, I, j, k. So this I hat is along the x-axis, j hat is along the y-axis, k hat is along the z-axis, and the hats, of course, tell us that we're talking about unit vectors. Anyway, our initial position is 3i hat minus 4j hat plus 2k hat in meters. And so my mass, which is initially at this position, moves to a new position, some r final, rf, equals to minus I hat plus 8j hat plus 6k hat. And remember, with that minus I hat, there's a 1 understood to be in front of that I, so it's minus 1 I hat there. Anyway, so this motion from R0 to RF takes place over an interval of 2 seconds. And the question in the problem is, what is the displacement of this mass? And then what is the average velocity of the mass? Now, the displacement is given by the formula for displacement. Delta R is going to be RF minus R0, and it's always going to be where you end up minus where you started. Where you end up minus where you started. So we can just plug in the number. So we've got our displacement value here, and so here's my R final, minus I hat plus 8j hat plus 6k hat in meters, minus my R0, which is 3i hat minus 4j hat plus 2k hat in meters. Now, what I want to do is notice that this minus sign in front of this parentheses will actually distribute inside here, and that'll make this minus 3, it'll make that plus 4, and then minus 2. And when I do the subtraction, I'm basically just going to be grouping like terms again, the I hat, the j hat, and the k hat. So I've got here a minus 1 I hat and a minus 3 I hat. They're going to group together, so that gives me minus 1 minus 3 I hat. I've got a plus 8 j hat. This minus minus makes a plus, so that gives me plus 4 j hat. And then I've got plus 6 k hat. This minus sign is going to come in here and make that minus 2 k hat. I've factored out all my unit vectors, and so then I can just combine these terms. And so my answer is that the displacement is delta r equals to minus 4 in the I hat direction, plus 12 in the j hat direction, plus 4 in the k hat direction in meters. And so that is my delta r, the displacement. Now to get the average velocity, we just want to divide the displacement by the time. And so the average velocity is going to be delta r over delta t. And my delta r, we have minus 4 I hat plus 12 j hat plus 4 k hat in meters. That's what we got on the previous part of the problem. And we're going to divide that by the time interval, which was given to be 2 seconds. And so 4 divided by 2 makes minus 2, 12 divided by 2 makes 6, 4 divided by 2 makes 2. So our average velocity works out to be minus 2 I hat plus 6 j hat plus 2 k hat meters over seconds, or meters per second. And that's the answer to the problem. Now let's look at instantaneous velocity, because this is really the more important thing that we want to be able to understand and calculate. And so again, we have our average velocity, and we can write that all out, but what we want to do to get the instantaneous velocity is take the limit as delta t goes to 0 of this delta r over t. And we know that as we do that, this line here is going to become tangent to the curve at the point of interest. So if we want to take this derivative by taking the limit, we're just going to take the limit as delta t goes to 0 of each term in kind. So I've got delta x over delta t. I'll let that delta t go to 0. The y term will have a delta t that goes to 0. The z term will have a delta t that will go to 0. And remember, when we say goes to 0, we mean gets arbitrarily close to 0 without ever reaching it, because you're not actually allowed to divide by 0. It's not a mathematically defined thing. So, but this is the process of taking the derivative, and so we can say that this v instantaneous again is going to be the derivative of x with respect to time in the x hat direction, plus the derivative of y with respect to time in the y hat direction, plus the derivative of z with respect to t in the z hat direction. So in each case, you just do it component by component, and you take the derivative with respect to time for x, y, and z. And this dx over dt, this would be vx, which in this case is the x component of v instant, or v instantaneous. This vy would be the y component, vz would be the z component. So these are the components of the instantaneous velocity. So really, just like you do in 1D, if you want the instantaneous velocity, you just take the derivative of the position function with respect to time. Let's look at another example. So here we have a position particle, r of t, so that means it's the position as a function of time. It's changing with time, and it's given by some x function of time in the I hat direction, plus some y function of time in the j hat direction, plus some z function of time in the k hat direction. And so we're going to have a specific example here. R of t is 12 meters per second times t in the I hat direction, minus, and this next term is big, it's in the brackets, 4 meters per second squared t squared minus 3 meters per second t. So that's all one term, and that's the function in the j hat direction. And so then for the k hat term, we just have a constant 15 meters. So this term's actually not changing in time, which of course can happen. So you could imagine something rolling along a tabletop, and so the tabletop is 15 meters high. That'd be pretty high for a table, but anyway, that's the idea. But the z direction isn't changing. As you know, it's constrained to move on this high tabletop, but the x and the y, this would be the x, this would be the y, as the time changes, the position of the particle is changing as well. And so given this, we want to find the position at t equals to 3 seconds, and then the instantaneous velocity at 3 seconds. Now the position is pretty straightforward. You just plug 3 seconds into this r formula up here. So everywhere there's a t, right there, right there, and right there. You just plug in 3 and do the math. And so when you do that, you should get some r of t, which is going to have an x component given by 12 meters per second times 3 seconds, so that's 36 meters in the I hat direction. The meters over seconds multiplies with seconds, and the seconds cancel, leaving you just meters as your units. And then in this term, we're going to have 4 times 3 squared, so that's 4 times 9, which is 36, so this is going to be minus 36, and then this is going to be minus 3 times 3, which is 9, so that's minus 9 in the j hat direction. And then this k hat term doesn't change, so we're just left with 15 k hat. And this is all going to be times meters and times meters. Should write that in. And so this gives me, my final answer gives me r of t is equal to 36 in the I hat direction minus 27 in the j hat direction plus 15 in the k hat direction, and all of those are going to be times meters. And so that would be my answer for r of t at t equal to 3 seconds. And of course, at some other time, I would just plug in whatever time I wanted, and that would be my answer. So actually, I probably should have written this as r of 3 instead of r of t, but that's what it is. Now for part B of this problem, we have our r function again, and we have the whole r function written out, and we want to find the instantaneous velocity. And the way we do that is we take the derivative of our r function with respect to time, and our r has been broken up into x, y, and z parts, and we're going to just take the derivative of each part in turn. And so the derivative of the x term is going to be the x component of the velocity, and so we call that vx of t, and that's the derivative with respect to time of the position, the x position. And the x part of this, the part that goes with the I hat, that's just 12 meters per second times t. And so when you differentiate 12 meters per second times t, you're just left with 12 meters per second. The t goes away. And similarly, when you want to do the y function, so my y part is this 4t squared minus 3t, and so when I take the derivative of this, I get minus 4 meters per second squared t squared plus 3 meters per second t, but you'll want to pay attention to the fact that I've taken this minus sign here and I've actually distributed it. So there's the minus 4 here, and then the minus makes a plus. So I get this 2 comes down and makes 8, so that gives me minus 8 meters per second squared. The 2 comes down and it leaves me with a t to the just the 1 power. And then this t goes away, and I'm left with positive 3 meters per second. And so when you're doing this, your SIGN signs, those are the things that are most likely going to trip you up. So you want to be very careful about watching those signs. And then for the z component, we have the derivative of z with respect to t. That's just that constant 15 meters per second, and the derivative of any constant is 0. So there is no v motion. So again, if this were an object that was rolling around on a tabletop, it might have velocity along x and y, but it wouldn't have any z motion because it's not leaping off the table. So the z motion is 0 in this example. So what do we have here? What we have is we have a function v of t that will give me the velocity, the instantaneous velocity of the particle moving along that position vector function at any time t. And so all we have to do is plug in the time. And there's really only one place where the time gets plugged in, and it's right there. And when you plug in 3 seconds, this is the answer that you get. 12 meters per second in the I-hat direction, minus 21 meters per second in the j-hat direction. And that is all there is to it. That's how you calculate instantaneous velocity.